professor in the College of Marine Science at the University of South Florida. His research focusing on large-scale ocean circulation and its impact on the climate. In particular, he has studied the Atlantic Meridional Overturning circulation and the Atlantic subtropical cell. Dr. Yao Fu and his PhD from Kiel University and the Gilmar Helmholtz Center for Ocean Research, Kiel, in Germany in 2018. After his PhD, he first worked as an assistant scientist at South China Sea Institute of Oceanology of the Chinese Academy of Science in Guangzhou, China, and then as a research scientist at Georgia Tech before joining the University of South Florida. So Atlantic Meridional Overturning circulation, AMOC, is a very active research topic in this building. I know Clark, Till, and Did published a paper just last month. So it's a good timing to have Dr. Fu here to strengthen our collaboration. Okay, let's welcome Dr. Fu.
Okay, thank you very much for the nice introduction. It's my honor to be here to give this presentation. So today I'd like to discuss with you about the Atlantic Meridional Overturning circulation and its stability. But first, let me ask you, I suppose that all of you have heard about the term AMOC, right? That's great. I seek information. That's a good start of the talk. So I think if you follow the news, right? So some of you may be very familiar with these news headlines that, like the Guardians, the Economist, CNN, and BBC, they're all talking about one topic and one topic only. That's the collapse of AMOC. And even the CNN wrote the most frightening sentence there. It says the collapse of the AMOC would affect every person on the planet. Right? And the BBC helps me to ask the question, will the Gulf Stream really collapse by 2025, which is this year, right? And of course, in the media, sometimes they refer to Gulf Stream as the AMOC, right? So now, with the question raised by BBC, I'd like to discuss with you the following topics in this talk. So the first one is, what is actually the AMOC? Right? And why it is important? And how do we measure the AMOC? And lastly, I'd like to talk about what is the state of the AMOC during the past few decades. And now, I'd like to begin with a little bit of history of the AMOC discovery. So there was a famous German expedition called the German Meteor Expedition in the 1920s. And the two photos here shows the very first version of the German research vessel Meteor. And here it shows the cruise track of the Meteor expedition. And as you see, the ship started from northern Germany and went all the way down to Antarctic. And on the way, the cruise completed 14 transatlantic sections. And they measured temperature, salinity, and even oxygen of the Atlantic Ocean. And this is also the first time in human history they used inverted echo sounder to measure the seafloor. And so when preparing for the cruise, Merz, who was the scientific lead of the Meteor expedition, gathered all the available data he could find in the 1920s and produced this plot, right? So this is the plot before the cruise. So he gathered all the salinity data and then made a meridional section through the Atlantic Ocean. And as you see, if you follow the salinity contours, you see some, you see that, the pointer. Great. So if you follow the salinity contours, you see there are water masses that are formed in the Southern Ocean, and then subducts to the intermediate depth, and then move northward. Okay? And you also see water masses that are formed at high latitudes of North Atlantic, and then sink to a greater depth, and then move northward. And so during the cruise, unfortunately, Matt was sick and passed away. And then his student, Wüst, took over as the scientific lead, completed the meteor expedition. Now, finally, after World War II, he published the findings, the data observed during the meteor expedition. And now you see not only the meridional flows, but also the horizontal circulation are inferred from the data. So at that time, they probably knew nothing about AMOC. But their pioneer work in ocean observation really laid the foundation for today's understanding of the overturning circulation. And 1922, that's exactly 100 years ago, right? And if you compare the salinity contour or salinity pattern meridional section with modern observation, you will be surprised to see that actually 100 years ago, the meridional salinity section they produce is actually very similar to what we today see with the modern observations. That's quite amazing, and this is how they have laid the foundation for our work. Now, I'd like to jump over 100 years of history and directly show you what is the AMOC. So, in general, the term Atlantic Meridional Overturning Circulation. So the term meridional means north and south, and overturning means there's vertical motion, right? So if you use this term, basically you are simplifying a complex three-dimensional circulation in a two-dimensional way. Basically, as indicated by the upper left plot, that you have a warm upper ocean water moves northward, and then you have a cold lower deep water flowing southward. However, in reality, the ocean circulation is far more complicated than just a two-dimensional view. People often forget that ocean is three-dimensional. So, in general, you see that the warm color arrows represents the upper light and warm flow that generally flows northward. But there's not only the meridional flow, but also there's zonal flow or drier circulation, which is driven by the wind. So when the water moves northward on the way, it loses the heat to the atmosphere, and the water becomes denser and denser. Eventually, in the subpolar and high latitude North Atlantic, the water sinks to greater depth and then moves southward, as indicated by this cool color arrows. And in this process, it releases heat and carries a lot of different properties, including heat, fresh water, oxygen, carbon, and nutrients, right? And it redistributes these properties on a global scale, and therefore the AMOC is very important for the global climate as well as marine ecosystems. So now, when we talk about climate change, we expect that the AMOC to weaken as the temperature gets warmer. And this is a model simulation, an ensemble of model simulation about AMOC in the past, but also with projections into the future. And as you see, in the future, the climate models generally predict a weakening AMOC. And as stated by the IPCC, so it is very likely that the AMOC will decline over the 21st century. And of course, it's not just the media, but also these high-profile journals favor a story about a weakening or decline or collapse of the AMOC. And but of course, the question that I am always very interested in is, what has the AMOC state been in the past few decades, during which we actually have observational record, right? So that's the question that I'd like to answer throughout this talk. Has the AMOC already started to decline in the past few decades, when we have observations? And with that question in mind, I'd like to introduce you some of my recent work and focus. So the overturning in the subpolar North Atlantic program, or OSNAP. So the OSNAP is a huge international collaborative effort, and we try to continuously measure the subpolar AMOC, and as well as the meridional heat and the freshwater transports. And so we have contributions from different institutions from US, UK, Canada, Germany, the Netherlands, and with some early contribution from France and China. And so for the OSNAP observation, we have two sections. One is the OSNAP West section, the other one is OSNAP East section. So the OSNAP West section covers Labrador Sea, connecting Canada and Greenland. The OSNAP East section covers the eastern part of the subpolar North Atlantic, connecting Greenland and the UK. And along the two sections, we have mooring observations. And along the moorings, we measure temperature, salinity, oxygen, and different properties, and also velocity. And so that we can, produce a AMOC estimate continuously over the past few years. And so here, I'd like to show you an example about what we actually measure along the moorings. I'm showing you here a mooring deploy log for a mooring at the center of the Meridional Sea. And along this log, you see, at the center of the log, you see a vertical line. That represents the mooring design. At the very bottom, there's a 4,000 pounds weight anchor, which basically is just a weight that fixes the mooring at a fixed location. And at the very top, you see a buoy. That's basically providing the buoyancy that drags the whole mooring upstream. And along the mooring, you see different instruments attached to the line. And there are 4 types of instruments that are typical at OSNAP observations. The first type is called acoustic Doppler current profiler, which is a current meter that measures ocean velocity for a certain depth range. The second type is a current meter that measures ocean velocity at a fixed depth. And the third type is called micro-CTD. So basically, we use that to measure temperature and salinity at a fixed depth. And the last type is typically a biogeochemical sensor, and typically like an oxygen sensor or PCO2 sensors. And so on this log, you also see when the mooring was deployed, as well as at what time each instrument went into the water. Right? So you see the handwritten notes here. And here are just 2 photos showing you what a mooring deployment or recovery looks like. So the first photo on the left, I believe it's mooring deployment because, first of all, the deck was very dry. Recovery, it must be wet. And then ADCP looks very new. That's another sign because after 1 year of the instrument in the water, the ADCP will be mounted with different sea animals or like the shells. The second photo, I'm not sure if it's deployment or recovery, it could be both. But in general, it gives you a feeling about how mooring deployment or recovery looks like in the open ocean. Now, with those type of observations, we can then generate a temperature section, salinity section, velocity section along the whole subpolar North Atlantic, and for each month. And now I'm just showing you salinity as an example. This shows you the mean salinity over the first 6 years of OSNAP observation. But we can do that for temperature and salinity as well. So by integrating then the velocity section zonally and vertically in density space, we can then produce the overturning strip function in density space as shown in this slide. So on the left-hand side, it shows you the overturning strip function in density space across the full OSNAP section, including both west and east. And on the right-hand side, you see the overturning strip function for across OSNAP West and OSNAP East separately. The thin lines represent the overturning slope function for each month, and the thick lines represent the time mean overturning slope function for the respective sections. And now, by finding the maximum of each monthly overturning slope function, we can produce or generate the so-called AMOC strength for each month. And by putting them together, I'm now showing you the most recent 8 years of OSNAP observations from 2014 to 2022. And the black line shows you the overturning strength, time series across the full OSNAP section, and the orange or red, when you see it from here, so that represents the AMOC strength across OSNAP East, and the cyan color, that represents the overturning strength across OSNAP West section. And first of all, we can see that the OSNAP East overturning dominates the total subpolar overturning in its mean and variability. And we see strong variability among the 3 time series. And most relevant to today's talk, over the past 8 years of observation, we see a relatively stable AMOC, which means that we don't see a collapse of AMOC, we don't see a weakening of AMOC, there's no trend. It's a relatively stable state. Now, next, I'd like to show you some examples about what we can do, or what we have been doing with the OSNAP observations. So the first study was to investigate the seasonality of the subpolar AMOC. As you see, the black line still represents the AMOC seasonality across the full section, red for OSNAP East and cyan for OSNAP West. And what we see is that the AMOC peaks in spring and has a minimum in winter. And this is the first observation-based study investigating the subpolar AMOC seasonality. And the seasonal change from the maximum to the minimum for the AMOC across the full OSNAP section is about 9 circles, which is quite large compared to its mean, which is about 16 circles. And as you see, again, OSNAP East dominates the seasonal variability of the total subpolar AMOC. And we further investigated the mechanisms responsible for the AMOC seasonality in the subpolar region. So this is just the same plot as in the previous slide. So the first quantity we investigated was the buoyancy-driven water mass transformation. So we know that buoyancy-driven water mass transformation forms the dense water that supplies the AMOC lower limit. And what we see is a maximum of transformation in the winter, and this transformation maximum is followed by the maximum of the AMOC. This is an indication that the dense water formation in the winter is responsible for the AMOC spring peak with a few months delay as the newly formed water is exported out of the basin and observed by the OSNAP observation, the OSNAP area. And secondly, we also investigated the role of wind in shaping the AMOC seasonality in the subpolar region. We find that particularly in the eastern subpolar basin, where the Ekman transport is very strong and it has a strong seasonality. And this Ekman transport seasonality in the eastern subpolar basin is responsible for the timing of the AMOC peak. So as you see, the seasonality of the Ekman transport here, and if you look back to the first plot, the dashed line now shows you the AMOC seasonality when the Ekman transport is removed from the seasonal cycle. And now you see that without Ekman transport, you will not see a distinct peak in spring. Rather, you see a relatively flat line from January to about May. So that's the role of Ekman transport in shaping the timing or shaping the seasonality of the subpolar. So that's about AMOC seasonality in the subpolar region. And now, with the seasonality determined, we have an 8-year time series. What we could do is simply, by subtracting the seasonal cycle, removing seasonal cycle, and then focus on the inter-annual variability. So here I'm showing you the two time series of overturning across Oceanography East and Oceanography West, but with the seasonal cycle removed. And then by superimposing a 1-year low-pass filter time series, now you see the inter-annual variability better. So next I will talk about the inter-annual variability of the subpolar AMOC. And to investigate the AMOC inter-annual variability, so I'd like to introduce you first a framework of the lower limb volume budget for the western subpolar basin and eastern subpolar basin. So the western subpolar basin refers to basically the Labrador basin, so the Labrador Sea, and basically bounded by the Oceanography West line. And for the eastern subpolar basin, it refers to the region between Oceanography East line and the Greenland-Scotland ridge, the GSR section. And here, the lower limb is defined as the volume below the time mean sigma mark. So sigma mark is the density at which you find the maximum overturning stream function. And here it shows you the different data sets we have used to conduct this study. And the lower limb volume budget is described by this equation listed below. So we consider every term that contributes to the volume change, to the change of the lower limb volume. So the first term is just d volume dt that describes the change of the lower limb volume with time. And second term, or the first term on the right-hand side of the equation, is the buoyancy-driven water mass transformation that basically adds water into the lower limb. And the second term on the right-hand side, that's the export. For the western subpolar basin, the export is just the volume flowing out of the basin below the time mean sigma mark across Oceanography West, which is equivalent to the overturning at Oceanography West. And for the eastern subpolar basin, we take into account both the water leaving the basin across Oceanography East in the lower limb, and also the water going into the water from the northern boundary. So, but because the variability is really dominated by the transport across Oceanography East, so the variability of this export for the eastern subpolar basin is still equivalent to the AMOC variability. Now, the last term is just a residual of calculated from the first three terms of this equation. Okay. I'd like to directly show you some results. I know that the time series looks very overwhelming. Please don't be intimidated by the time series. I will walk you through step by step. But so here, the upper plot shows you the volume budget analysis for the eastern subpolar basin. The lower plot shows you the volume budget in the Labrador basin. The volume budget equation is placed in the middle as a reminder. Here, the volume change, the volume dt, is shown in green, and water mass transformation in red, export in blue, and the residue in black dashed line. So before talking about inter-annual variability, I'd like to first draw your attention to the time mean volume budget by looking at the time mean residue. So here, for both the eastern and western subpolar basin, you see a time mean residue of about 2 circles. So this basically means that we can close the volume budget using the different independent data sets that I showed in the first slide, and close the budget within about 2 circles. And this is quite remarkable, especially for the eastern subpolar basin, where you see the AMOC, or the overturning strength, was about 16 circles across the Oceanography East line. Now, after talking about the time mean residue, I'd like to walk you with you step by step about the inter-annual variability of the AMOC. So, because there are different terms, and this is a volume budget, and I'd like to simply use a lead-lag correlation analysis to investigate the relationship between the different terms in the volume budget. So the first two set of comparison is between the buoyancy-driven water mass transformation and devolume dt. Here we see that transformation and devolume dt are maximally correlated at zero lag, because we know that transformation adds water into the lower limb, right? So then this zero lag correlation basically means that the lower limb volume has an immediate response to the water mass formation due to RC interaction. And the next set of comparison is between buoyancy-driven transformation and the export, or the overturning. And we see here that in both the eastern and western subpolar basin, transformation is maximally negatively correlated or anti-correlated with the export or with the overturning. So at this point, I think we could, and also of course, I forgot to mention that transformation leads the export by a few months. So at this point, if you could imagine, basically, we could expect a relationship between the three terms, right? So transformation adds water to the lower limb, and then that will immediately increase the lower limb volume. And then a few months later, we see an enhanced export of the water, right? Does that make sense? And then, then we need to verify if this is really the case by examining the relationship between the volume change and the export. And interestingly, we only find a reasonable relationship in the eastern subpolar basin, where you see that the devolume dt is maximally anti-correlated with the export. When the devolume dt leads the export by a few months. But in the western subpolar basin, we don't see a significant correlation between the two. So this basically means that this relationship is only valid in the eastern subpolar basin, as briefly summarized here. So by taking advantage of the first 8 years of oceanic observation, we focused on the intended variability. And then through a lower limb volume budget analysis, we only see the expected relationship in the eastern subpolar basin, where we see an enhanced buoyancy-driven water mass transformation, increases the lower limb volume, and then a few months later we see enhanced export or overturning. But this relationship is not clear in the western subpolar basin. Now, after showing you some examples about what we have done with the oceanic data, I'd like to bring your attention back to the stability of the AMOC. As I mentioned earlier, so using 8-year data, we don't see a decline, we don't see a collapse of the AMOC, and AMOC was relatively stable. However, we know 8 years is still relatively short, it's not long enough. So then I'd like to introduce you another study of mine that investigates the AMOC state over the past 3 decades by using repeated hydrographic section data and combined with satellite altimetry and also a simulation model. So the 3 sections we used are listed here. So we have the first Labrador section, which is primarily based on the World Ocean Circulation Experiment AR7 West line, which is very close to the Oceanic West section. And the second section is the Eastern Subpolar North Atlantic section, which is primarily based on the World Ocean Circulation Experiment AR7 East line, which is also very close to Oceanic East section. And the last section in the subtropical region is primarily based on the WARS A05 section, which is very close to the rapid AMOC observation. And one of the benefits of using hydrographic sections is that we can not only determine the AMOC strength, but also have information about hydrographic property changes over the different times during the time we are interested. And the 3 sections I choose are very close to the mooring observation or the area observation. So the area observation provides a very important validation for the AMOC estimate based on hydrography. So first of all, let's look at the water mass property changes over the past few decades. Here I'm using salinity as an example, but I also have data for temperature and also even oxygen. So because I have many repeats for each of the sections, what I can do is simply calculate a decadal composite for the 1990s, for the 2000s, and the 2010s. And then I simply make a difference between the different decades. And I've always used the later decade minus the 1990s. So the 1990s is used as a reference. And in the upper plot, you see the salinity difference between the 2000s and the 1990s. And the lower plot shows you the salinity difference between the 2010s and the 1990s. And as we see in the upper eastern subpolar basin, there's very strong salinity changes over the past decades. And first it's getting saltier, then fresher. And not only the upper ocean, but also at the intermediate depth, where the laboratory water layer, we see a gradual salinification. And also at the very bottom, the overflow water layer, we see changes over different decades. And of course, at this point, we are naturally assume, I would first naturally assume that, we see dramatic changes in water mass properties. Probably the AMOC also changed very dramatically over the same time period. And so let's find out whether it is the case. So there's a method called the box inverse method or box inverse model. This method can be used, can be applied to hydrographic section data and then to determine the circulation. I will not go into the details about this method, but in general, the idea is that to form a box, an enclosed box, by using hydrographic sections and the ocean boundary, and then by conserving the volume of this box, we can find the most suitable solution and therefore determine the circulation. So by doing that, I combined the subtropical and subpolar region together, form a big box there. And because I have many repeats for each section, in total I can build 8 boxes throughout a period from the early 1990s to the mid-2010s. So then I'd like to directly show you the results of this box inverse method analysis. First, we look at the estimate in the subtropical region. So in the subtropical region, we have rapid observation, which is shown in red. And the rapid starts from 2004 and continues even till today. So that provides us basically the longest, AMOC, direct AMOC observation record, and that's shown in red. And the green line shows the estimates based on GECO2 simulation product. And the stars with arrow bars, that represents the estimates based on hydrography. And now if we compare the AMOC strength in the 1990s and the 2010s, what we see is that they are not substantially different from each other. And this basically means that at least in the subtropical region, we don't see a clear weakening of the AMOC. Now let's move northward to the subpolar region. And again, the orange line shows you the first 2 years of OSNAP observation. That was the data I had back then when I conducted the study, the very first 2 years. And the gray line is again the GECO2 estimation. And the stars with the arrow bar are the hydrography-based AMOC estimates. And again, when we compare the AMOC strength in the 1990s and the 2010s, we find that they are not substantially different from each other. And additionally, we also see that the overturning in the eastern subpolar basin, which is shown in the upper plot, that's dominating the total subpolar overturning with a strength of about 16 circles in comparison to the OSNAP east, or the larger sea overturning is just about 2 circles. And this is consistent with the modern OSNEP observation, but extend the record back in time on decadal timescales as well. And then, of course, GECKO2 overestimates the overturning strength in the rubber seam, and that's a common problem of many models, not just ocean model, but also climate models as well. And in total, now when we combine the 8-year OSNEP observation and also the hydrography-based AMOC estimates together, we could say that the overturning was relatively stable over the past 3 decades. And finally, I'd like to summarize the story by using a bad news and a good news. We can go with bad news first. So over the past few decades, right, we have seen dramatic changes of water mass properties. And this could be a consequence of climate change, or it could be also climate variability. But the good news is, so far, we still don't see a declining AMOC or collapse of the AMOC. But if you combine these two news together, we find an interesting conclusion, which is that the overturning strength and water mass properties are decoupled to a much higher degree than we previously thought. And right, so that's basically the end of this talk. But now let me ask you the same question again. Will the AMOC really collapse this year? Give me an answer. Right?
Yes.
Oh. Right, so I can now tell you with confidence, based on my own research, right? The answer is no. And so we don't believe that AMOC will collapse anytime soon. At least that's based on what we see in the past 3 decades. AMOC was relatively stable. But of course, I mean, anything has a but. So this slide serves as a disclaimer. I'm not here to say that the climate is not changing, nothing has happened, and we need not to worry. But on the contrary, as we speak today, the ocean continues to warm, Arctic sea ice continues to melt, and so the climate is changing. So the message in the end I would like to convey here is really that instead of spreading those nonsense, I think we really need to understand what has happened in the past, and the knowledge we gain will lead us into the future. And yeah, so these are some next steps that I'm focusing on. For example, by investigating the role of the wind in driving AMOC into any variability, and also the impact of the freshwater anomalies on the AMOC in the subpolar region in observation and also climate models. And there are some long-term plans, but I will not read them. So finally, with the modern version of the meteor ship, I'd like to thank you for your attention. Thank you.
Okay, any question from our students first? Okay, Evan.
This is a little bit more of a modeling question, so not what you talked about, but maybe you know because I don't. So you talk about overestimation of the Labrador Sea component to AMOC circulation in those models. Do you know whether those strong declines that you see in the projections are they coming from the Labrador Sea, where the Labrador Sea is decreasing? Or are they coming from the eastern side of the basin?
You mean referring to the western part based on
Exactly,
right?
exactly.
Yeah. So what I understand is really that in the 1990s there's a strong NAO event, so that persists over a few years, even roughly a decade. That's where you see the 1996, 1995, and 1997, that's when the NAO was the strongest. And then, of course, you see a strong convection in the Labrador Sea, and then the model will project a stronger overturning in the Labrador Sea. While in the 2000s, and then later in the 2010s, probably in the model there was not such a strong NAO event, and then you would not see a stronger overturning in the laboratory. So I'm not sure if that's really like a projected by the climate models that you have a steady decline of AMOC, or it's just basically a decadal variability in Gecko-2 simulation, because Gecko-2 is a state estimate. It has observed temperature and salinity in the model, and so I'm not sure about that question in the end, but that's what I could try to get. Thank you.
Okay, open it up. So actually, I have one question. So like if you go to some meeting, right, and you are in the same room with people that's kind of an advocate, okay, the AMOC is collapsing. I mean, do you guys even talk?
Oh yeah, I mean, the other day at the EGU meeting in Vienna, I met Caesar, who published one of the Nature papers. So here. Okay. Yeah, that's the first one. So I met her, and after she gave a presentation there, I basically asked her a question about, so there's an observational group, and there's a paleo group or modeling group, and it seems like the two people from two groups never really care about the research from each other's group. Do you have a comment? That's my question to her. And I think in the end, what she answered was similar to what I think is basically that I think the different groups of research groups should talk more to each other and try to understand what is the problem of each other's estimates. So for the observation, as I am, we have limitations too, because our data record is relatively short. As you see, the direct AMOC observations in the subpolar region is just 8 years. And in this year, we are getting data, 2 additional years of data, making it a full decade of observation. But still, that's nothing if you are interested in decadal variability or long-term trend. So I think in the end, it's just a question of how much we would like to work together to figure out the problem we are facing together in the end.
More questions? Yes.
So, thank you very much. Excellent presentation. I'm still wondering what the overall implications are, especially regarding climate and action in the future.
Yeah.
Do you have any, if not recommendations, then just guesses, what, or you yourself, how would you embody, enact your own climate actions in the future?
Yeah, I mean, so of course, the most important thing is really to understand what's driving the changes of the ocean. So I think one of the main idea or main thing behind this research is really to understand whether the ocean has changed, or to what extent it has changed, and why it has changed. Right? So for that, I think that's the first thing we need to understand. And until today, I think we don't really understand that very well. So we have a lot of climate models, but I wouldn't say the climate models are wrong, but at least there are a lot of problems with the model. So I think the first step is really, I mean, on the other, if we step back, think about why we're developing models. So I think we develop models because we want to, in the end, be able to predict the future without spending money in observations. But the promise is that we need to first understand the dynamics. We need to understand why or what is driving what, right? And I think in the end, so the research based on my own, basically, we're trying to understand, using the observations, what's going on. And I think this will provide a very important reference for study using the climate models to serve the ultimate goal, which is really to understand or to use model simulations to predict the future.
Just thanks for the talk, I appreciate it. So in the observation system that's been set up, is there like a lifetime or longevity of that? I mean,
Oh, yeah.
They've been there 8 years, is it something that has to be, does the instrumentation have to be replaced pretty often? Does
Right.
it have a 25-year lifespan? What can you kind
Yeah,
of expect from
so
it?
we exchange or recover the mooring every 2 years. So the mooring stays in the water for 2 years for each deployment, and then in 2 years we just recover them and redeploy them. So the instruments, most of them are reusable, but sometimes some impact of whatever reasons, due to pressure, long-term pressure in the water, can cause damages to the instruments. But overall, we exchange them every 2 years, and then we recalibrate them on board. And sometimes, if the data seems very off, then we just bring them back and then use a new instrument to replace that. And but in terms of the project, so we have so far funding till the end of 2026, and we are seeking for new funding from NSF, but we don't know.
What Elon Musk had to say about that.
So presumably these, like the buoy at the top would be pushed by wind. Is that like taken into account with the data if it's like angle versus being straight?
Yes, so if it will not be knocked down by the wind, but rather knocked down by a strong current.
Right.
And then because the mooring is totally under the water, so there's no component above water. So typically the nearest, the shallowest instrument is like 50 meters below the surface. But if there's a strong current or an eddy, right, so it can knock down the whole mooring by a certain degree. And then what we need to do is to take into account that problem. And so basically, like if you look at the pressure record of the instrument, you see that if there's an eddy passing through, then you see a drop of the pressure, basically going deeper and then comes back again. So something like that. But because in terms of velocity, so that basically we measure the velocity using ADCP, and then we can kind of rotate because the beams are like 4 beams, and then we can basically rotate the vectors to the north and south direction, to whatever direction we want. But then when a current or eddy passing through, so the velocity measurement will not be at the same depth as the design is supposed to.
Okay, Evan.
Yeah, if you could have any new observation, like, infinite resources to do something new,
Yeah.
what do you think would be like the most useful place for new information to be able to better constrain this?
Yeah, I think I would put some moorings at the very bottom of the ocean, where the dense water formation really happens. So where not just the formation due to air-sea interaction, but rather along the continental slope, like the overflow waters, where the models are really doing poorly, or around Antarctic, where the bottom waters are formed, and the models are doing poorly. So I would really put money into those places where that will help us to gain a better understanding of the process, and then that will ultimately improve the model.
Okay, let's thank our speaker again. Thank you for coming.